Welcome back, Precalc. In today's video, we're going to jump into 4.7 where we're discussing the inverse trig functions. And before jumping in, I have some review stuff here up on the board. What I want you to do with your team, your neighbors, whomever you're working with, is I want you to attempt to do two things for me. First, I want you to fill in this blank right here. And second, if this is a graph of f of x, I want you to fill in this blank right here and to graph the inverse function if possible. Cool. I'll give you a head start on that, and you will see that back in just a moment. All right, so we already did the intro, and I don't remember what it was, but a couple spots here. I see that on this first little point, I have function, we'll start here. Give me a function f of x, and I'll tell you its inverse is also a function that we'll call f inverse of x if and only if f of x is what? What's the word I'm looking for? One more time? Lot a bit louder. Not a little bit, but a lot of it. Positive. I'll tell you, I think that this thing is negative here, but I do think the inverse exists. There's some really, really fancy word that we use. Or you draw a small Star Wars ship. If I was going to draw a TIE fighter, I'd start with the vertical wing. Now that's not a starfighter in reality, or weird. That's not a ship. That says if a function is what? 1 to 1. Anybody recall what that means? For every 1x, or every 1y, how many x's map to it? 1. It's 1 to 1. We can write it like this. The language that I prefer is injective. That's the nicer language, or the more formal language. And then if you want it, the other way that we could talk about this is if it passes the something. Vertical line test tells me if it's a function. What tells me if it's injective? The horizontal, because I cannot let any more than 1x map to each y. Passes the horizontal line test is the third way to do it. Now, we have looked at inverses a few different times in here. We saw earlier this year, the first inverse I believe that we looked at was exponentials, and their inverses, the logarithmics. So we saw those undo each other. We saw, I'm trying to remember if we really did see it, but we've used it, squares and square roots, cubes and cube roots, so forth and so on. Okay, so a couple things. As we're checking whether or not two functions are inverses, they better do this. If you compose them with each other, they essentially just undo each other. That's super duper important. Now, beyond that, this is really formal. The domain of f is the range of f inverse. Just to stir the memories here, the domain of f is a set of all what that we can use? X values. Okay, the range of its inverse is all the y values. It's like they literally just swap places, right? Now, the reason that I care so much about this will become pretty apparent over the next couple minutes, but notice, domain of f becomes a range of the inverse. The range of f is the domain of the inverse. We're going to use that. Anybody remember this part? If I wanted to graph the inverse without actually finding it, could we? I'm going to challenge you guys. If you have it in your memory, awesome. If not, I'm going to say go way back. Find it. It's in your notes. I guarantee it when we graphed inverses. I got to think of where it is. Cool. I'll give you guys a second. When we graph these things, we are reflecting over the line y equals x. Now, to make sense of this, I am going to draw a really faint line here so that we don't have to try to parse it out. But without a scale, would you believe that that's y equals x? And can you guys see that little gray line? Okay. Now, remember, we used this to our advantage. We did it a lot when we were graphing logs and stuff. If this is the point 0, a right here, and the domains and ranges just flip, all the x's and all the y's. Don't write this point. I'm just using it to help me out. If this is the point 0a, what point is on its inverse? And that is incredibly hard to see. If 0, a is on the graph of f, what's going to be on its inverse? If louder? a comma 0. All the x's and all the y's just swap places. Now, in reality, we don't need to do all of that because I can see this gray line. Can we reflect over it, at least roughly? So check it out. Looks like it does something like this. Oop, I'll make that a little bit nicer. Something like this. It's not perfect, but does that kind of look like it's the reflection? Now, if you can do this and you can reflect, everything that we're going to do today is just an extension of this idea applied to the world of trigonometry. Cool. We can graph an inverse, no problem. Everybody okay with just that quick review of stuff? Awesome. So, moving forward, we are going to be looking at inverse sine. And I don't love prepping. What did I just do? I don't love prepping them all because I don't want you guys to necessarily write all of this stuff down. However, we are going to jump in right here at inverse sine. So I want you to get the inverse sine function. A rough sketch would be okay, but it's not necessary. And then the last little piece, this, I don't care if you write down, but I want us to think about this piece. For the inverse to exist, we have to do something. I'm going to give you a moment to let you catch up. And if you guys will, I don't know, put your pencils down whenever you're caught up. Optional to graph this, optional to write this part down. I'll give you just a moment. We'll catch back up momentarily. Here we are. We're looking at this graph. Now, right now, if I said this thing has an inverse, you probably believe me because you've seen inverse trig stuff before. Whether it was in geometry or algebra 2, doesn't matter. You have seen it. The bigger question is, if I want to write it using f inverse of x, it had better be a function. If I were to take this thing right now and try to reflect it, will it work? So don't draw this one. I'm just going to try. Ooh, so let's see. These are not square graphs, so I got to think this out. This is the point 0, 1, right? Which means y equals 1 must be right about here. So this is the line that I'm trying to reflect over. Do not graph this, okay? I'm going to undo all this here in just a second. If we tried to reflect this, let's just see what happens. I'll start here, and it looks like it does something like this. Whoop. Something like this first, right? And it does this. I can't do it all the way. I'm going to have trouble, but I can already see there's going to be an issue with it. When I try to do this, it's not going to pass the 1-to-1 or that vertical line test. It just won't. And I know that it won't even without having to try to think about it. What do we say that only has an inverse that's a function if and only if what? One more time. It's 1-to-1. Injective. Give me the graphical version of that. If it passes a horizontal line test. Now, right now, I think it might. So looking at this, I was trying to think ahead a little bit. How many periods of sine do we have showing? We have 2? 1. It goes 0 to 2 pi, right? You do not need to draw yours, but I want to look at this one. If I tried to do this, obviously it fails, right? So I might have spoiled the question. For this to work, we could need to restrict the domain. Now, I'm going to draw just a little bit of extension here. I know that this wave keeps going. You don't have to draw yours. I know it's going to keep going like this, and all of a sudden it fails, right? So here's what I kind of spoiled it. We can keep that here. To make an inverse function exist, and we'll switch back to this red. For f inverse of x to exist, we only use a portion of this graph. And I'm going to say a piece because it's the same idea, some small interval of this graph or the graph. So here's what I want you guys to do. With your neighbors, I want you to determine which portion of this graph could I possibly use in order to make this thing 1-to-1. Okay, you should take your marker, your pencil, whatever it is you're writing with, make it bold, and if you think it's here, I'm okay with that, but if that's where you think it is, bold it on your page. I don't think it's there. Find me a restriction that will work to make this thing 1-to-1. I will give you just a moment. Talk it out with your neighbors. Be able to convince me. Looking at this, it was definitely not this first little section right here. It just didn't work, right? Why doesn't this one work? Does it pass the horizontal line test? That was not horizontal, but I can already tell that it doesn't. Okay, so you guys hoot and holler whenever you want me to stop. Stop, or start rather. That's a weird way to word it. Okay, and I'm going to start rolling here, and you shout out when to stop. Now, once I get there, have I hit every possible y value that sine ever spits out? Now, we're going to see this happen over and over and over because there's infinitely of these many intervals that we could use, right? I could use pi halves to 3 pi halves. Could I use 3 pi halves to 5 pi halves? And so forth and so on. I could use any of those intervals because I'm going to get just that portion that hits them all. Now, for our purposes, we're going to be a little bit nicer than that, and let's jump in. We will restrict, instead of pi halves to 3 pi halves, which is fine, is there a nicer interval? So if I look here, this interval's fine. If we just look from, we said pi halves to 3 pi halves. Less than x is less than 3 pi halves. Whoa. Pi over 2. Okay, that part works fine, yeah? Is there another part that might have worked nicer? So start from the bottom and go to the top. So we would need to move over one whole piece, right? So if I start at like negative pi halves, for example, where should I run to? If I run to pi halves, is that the same idea that we just saw a moment ago? Now, check it out. By restricting, and we're going to pick that convenient one. This graph didn't allude to it, but we can still see the same idea. We can restrict, or we do restrict, sine of x on the interval, and there's infinitely many of these that we could pick, but which one did we just restrict on? Good. I'm going to include those points from negative pi halves all the way to pi halves to ensure 1-to-1. We can restrict the domain anywhere that we want to make this work, and I'm going to use the one that winds up centered around the y-axis, but it's the same idea. Now, looking at this, we ensure that this is 1-to-1. Right off the bat, if I'm going too fast as we start rolling, let me know. We're going to look really in depth at sine, and then the other 5 just come for free. It's the exact same logic as we roll through it. Let's give ourselves one more little part. The inverse of sine is, how would you word the inverse? We've used this language already. Inverse sine, or not cosine. Whoever said a good thought? Not cosine. That's the cofunction. I'm going to use first one. I hear a bunch of secants and cosecants. You guys are on the right track because you're giving me trig stuff. But I think as soon as I start writing this, it's easier. The inverse of sine can be written like this. The arc sine of x, or, and this one, you do not have to do it exactly like me, but it drives me crazy that this isn't the convention. I'm going to use a capital S when I'm doing it to indicate that this is, in fact, our inverse sine rather than 1 over sine because of the way negative exponents typically work. This is how we're going to write our inverse function. Now, from here, I'm going to star this. This is an important guy. Okay, if you ever have the desire to say sine to the negative 1, you get 10 seconds of amnesty right now to say it. I don't want to hear it again. Sine to the negative 1. Cool. All right. Now, looking at this idea, we have it written out. You guys have seen inverse trig stuff. I know it. I don't know if we've done it this year in here yet, but we're going to start right now. So check it out. Right in, we're going to get one more really important idea. Defining, I'm going to say definition, DEF apostrophe N, of inverse sine. And I'm going to say arc sine. Okay, for this, couple nice things that we're going to be able to deal with. We're going to say that y, some function, is equal to the arc sine of x, or the inverse sine of x. If and only if. And I all of a sudden have this very logarithmic feel because this is almost exactly the same way that our definition for logs worked. Okay, hypothetically, just using what we know about inverses, if I asked you to solve this for x, how do you undo an arc sine? You take the sine, right? It's not a multiply by, it's you literally take the sine of each side of this function. Now, I'm going to go out one little step here. If I took the sine of the left, do you guys agree it would now be the sine of y on the left side? What would remain on, or what would be, I try to avoid left and language. What would remain on the right side of this equation? X. This is it. Now, we have the arc sine of x if and only if the sine of y is equal to x. From here, couple little parts that we need to be very mindful of. Where we are going to say that the domain of arc sine of x is equal to, and we're going to pause for just 1 second once we get here. I'm asking about the domain of the inverse, which is the same question as asking about the range of the original function. Wherever we decided to cut our sine function when we looked at the graph, what do the y values range from? What's the lowest y value that shows up on this? -1. What's the biggest y value? So the range of this function is -1 to 1. That means the domain of its inverse ought to be -1 to 1. Okay, I'm not going to write this part down, but I want us to internalize this on a deep level. If I ask you to take the arc sine of anything bigger or smaller than 1, like -2, can't do it. Cannot do it. Whatever x we're plugging in, whatever angle, it needs to be between -1 and what? 1. -1 to 1. Okay. Beyond that, what do you think the range of arc sine is? Ooh, it can't be all real numbers. Where did we have to restrict sine to make this work nicely? From -pi/2 to pi/2. Now, we could have done pi/2 to 5 pi/2 as well. Or 5 pi/2 to 6, 7 pi/2. Weird. Okay, we're going to work on this typical way here. We haven't even started solving it yet. These ideas are going to burn people. It's not so much of a trick question as just a check, do you understand? Inevitably, can almost guarantee, quiz, test, I suppose we're near the end of the chapter. I'm going to ask you to do one that you cannot do, that looks like you can do it, but you can't. We'll even see one today. Cool. Before we start doing some examples, definition feel all right? Now, it won't show up today because we're not using it, but I want to just make sure this is another talking one. We use SOHCAHTOA if you give me an angle and a side to find the other side. That's what SOHCAHTOA does. Inverse, instead of saying given an angle and a side, it says given me two sides, let's find the angle. We are looking for angles when we use arc sine. And I lied. I am going to put that in really obnoxious. Arc trig allows us to find angles. Before, SOHCAHTOA, trig in general, used to find a side. Arc trig finds the angles. All right, we are going to do some examples. And let's see, what color is arc sine typically? Oh, okay, we'll switch to a different red. Example. We're going to evaluate each of the following. Cool. So, I'm going to have A, B, and C here just so you're aware. Let's check our first one. I want us to evaluate the arc sine of -1 on, and I'm going to give us an interval, -pi-halves to pi-halves. Our regular old interval where it's centered. We're going to start seeing solve this on this interval more and more frequently. If I'd chosen pi-halves to 3 pi-halves, it would work as well, but we'd just be looking for a different place. Cool. Right off the bat, we're going to take these real slow right now. First thing I'm always going to check when I'm evaluating arc trig stuff. My argument of this arc sine is -1. Is that within the domain of arc sine that we just determined? Yep, so I'm cool with it. I can actually work this out. Now, anybody know the number off the top of your head? Super confidently. That's okay. If I don't know it, can I just say it's something and we'll figure out what something is? I'm going to set this equal to some number. I'm just going to use x. I don't know what it is yet. So let's suppose for now that it is equal to x. Means I can then write the arc sine of -1 is equal to x. Don't know what it is yet, but there must be a number because it's in the domain. I'm sorry. Cool. Well, shucks. Did that really help? Oh my, sine of both sides? Love it. You do not have to write this. I'm going to write it this one time, and I'll probably do it again, but I'm going to try my best not to. If I take the sine of the left, and I take the sine of the right, and I'm just going to go ahead and do this, because look at me learning how to technology. Almost. It was a good idea, right? Oh my gosh, it was a terrible idea in hindsight. We're just going to write it. If I take the arc sine, or the sine of the left, I get this expression. The sine of the arc sine of -1 equals the sine of x. On the left, what happens? The sine of the arc sine. I'm okay with it in this one context. They cancel. They undo each other is what I'd rather call it. And check out where we're left with. I'm going to switch sides, but that feels like we're looking at a different problem all of a sudden. We have remaining the sine of x is equal to -1. Okay, unit circle memory game, going to become super valuable now. Is there a somewhere between -pi-halves to pi-halves, the right side of your unit circle, where sine is -1? Check it out. If you don't have it off the top of your head, unit circle, very front page of your textbooks if you have your book out, or ripped out of your book, or printed. Is that printed or ripped out, Sean? Thank goodness. It stressed me out. It looked like, because I ripped one out years ago and I immediately regretted it. But cool. All right. On this part of the circle, is there anywhere where sine, the y value, is -1? It's at -pi-halves. So check it out. This happens at x equals -pi-halves via the unit circle. So therefore, and I'm not going to make you guys do this really formally, but especially our first example, we should. What we have just determined is the arc sine of -1 is apparently equal to what? -pi-halves. Boom. We have it. We've used the definition. Things are good. Feeling all right. I want you guys to do 2 practice ones for me. Before I just cut you loose here, I'm going to show way less work, just so you know. Are there questions, or what questions do you have about any part of what's just happened? If you're on arc sine, you want to think the right half of the circle. Cool. So, couple more for you guys. Video people, you're going to see some editing magic. So here are B and C for anybody watching the video. I want you to pause it now. You're going to see detailed solutions in 3, 2, 1. All right, looking at it. Here's my first step. Right away, sine of x is √3/2. Is that further up or further right? And is ooh, are you sure? √3/2 is way up high. Because we're looking at sine. Is that x or y? So y needs to be higher up. There's only one place where it's positive root 3 over 2. This is at, and I'm just going to say sine, the arc sine of root 3 over 2. Where's the only place that happens? Pi thirds. Now, another good check. I know that the input needs to fit in the domain that we've restricted. The output better fit in the range. Is this between negative pi halves and pi halves? Which is what we said the range should be, my output. We're golden. Okay. One more, part C. Talk it out. Who has pi fourths? Good. Why not pi fourths? Because it's not root 2 over 2. What is the domain of arcsine? The range of sine. So negative 1 to 1, yeah? What's the square root of 2? Is it bigger than 1? Boom. So, I'm just okay with this. I'm going to say no. No. Specifically, no solution. But no, this input not in domain. We can't do this problem. There's nowhere on the unit circle where sine is root 2. Just doesn't exist. Root 2 over 2 is fine because that's less than 1. But root 2, never happens. Awesome. Feels okay, feels awful. All right, I have a new challenge for you guys. I'm going to need my notes back for just a second. I just need my setup. Okay, I'm going to give you guys a little bit of time. We are going to divide and conquer, I think. I am going to steal this because I want you guys to go think about it. But I'll get these back in just a minute. Okay, we're going to divide and conquer. We have looked at the graph. Just kidding, we haven't looked at the graph yet. We will look at the graph. Graphing them is wonky. We'll get there. From these, we have looked at inverse sine up to now. What other inverse trig functions? Oh, I was way off of half, huh? What other inverse trig functions? I also was way off of a straight line. What other inverse trig functions do you think exist? Probably all the 5 other ones, right? So check it. I want you guys to do me a favor. Other inverses or other inverse trig functions. Blech. Okay. We are going to do a couple of things here. I want you guys to find me 2 more. And I lied about splitting it up. We'll just all hit them here. I want you guys in no particular order. What we just did as far as defining it, I want you to do the same thing with cosine and with sine. Your task right now is for the cosine, and I said cosine and sine, but I definitely meant cosine and tangent. I want you to have a section for the arc cosine, or y equals arc cos of x. And I want you to do the same thing for the arc tangent. Now, I'll get some graphs up on the board, but you're going to give me a definition, a domain, and a range. That's what I'm looking for with this. For the arc cosine and for the arc tangent. Or the graph y equals arctan of x. You are going to find me, again, the definition, the domain, and the range for each of these. Now, what I'm going to do is pause it here. I'll use a little editing magic because it probably will be nice for you to have the graphs of these available also. I'm going to come back to the screen in just a moment. Here is the parent function of cosine x. When you're ready, let me know. I'll check, and we'll throw out the graph of tangent as well. All right. Where do you restrict cosine? What does its new domain and range become? Put those in for your arc trig. I'll give you a minute. As we're looking at this, the domain of arc cosine based on this restriction here is just like we saw before, right? Okay, the domain of this function should be from -1 to 1. Which part of the circle are we looking at if we're thinking arc cosines? I think we're going to see the top. We're going to see y here in just a second. For the range of this, where to where? Where was our restriction just happen? From 0 to pi? Cool. 0 to pi. Okay. This part we have to have. Y is equal to the arc cosine of x. And I'm going to use different notation. This is the same thing as if and only if. This is a biconditional implication. Both ways. If and only if, what's true? Cosine of y must be equal to x, right? I'm just going to take the cosine of both sides, and cosine of y equals x. Cool. Arctangent, a little easier, a little harder? Same. I'm going to go over to the graph of tangent, and I'm going to keep cosine up there just so we can make sure, without labeling it, I can see where pi's and things are. Cool. I'm going to ask you guys for tangent. See if you can do the same thing. Baller. I'm here. Sean, spot on. What's different about this? You said the range. The range of my tangent function is all real numbers. How does that relate down here? The range of tangent is all real numbers. Good. The domain of my arctangent then, I'm just going to say domain, all reals. We can use infinitely many of them, all real numbers, because I'm just looking at the range of this. Okay, what is a restriction you would like me to put on this to make sure that it's one-to-one? Because right now it's certainly not. Any horizontal line touches infinitely many tangents, or parts of the graph of tangent, but I can restrict somewhere. Where? I like negative pi halves to start. And you said we'll start there and go to pi halves? I think that's going to work. Is that one-to-one? Now, just so you can see, if I had done this a little bit differently, so maybe I go pi to pi halves, or 0 to pi halves. Oh my goodness. That doesn't quite cover it, does it? And then if I try to be, oh, well, I'll just be a little clever, I'll just go to pi. That kind of does it, but in a really weird way. Would you agree? The nicest place that we can get was exactly what Fern suggested. Let's go negative pi halves to pi halves, eventually. Boom. Okay. The fact that I've just restricted it from negative pi halves to positive pi halves for tangent of x means that we've just discovered the what of the arctangent? The range. The range of arctangent is the domain that we've picked. So we just saw here, where does it range from? Okay, here's our big moment. I'm not going to put my marks on yet. Negative pi halves to pi halves. What happens on the graph of tangent at negative pi halves and at pi halves? It doesn't touch. It's infinitely close. There's an asymptote, which means, can you ever actually include these points? So how do I indicate that? We parenthesis it, or less than instead of less than or equal to if you're doing that notation. Cool. What is the definition of arctangent? Y equals the arctangent of x if and only if say it again? Good. No, I'll stick with the same way. Tangent of y equals x. Now, same thing here. We don't really have to worry about the domain part because tangent's going to work anywhere that we pick. But as we're looking at it, I want you to get a few examples and some practice with these. So here we go. I'm going to give us the next 10 minutes. Do you think the examples that we do with arc, cosine, or arctangent are going to look any different than what we just did with sine? You're literally just going to write a different function, right? So we're going to see how this goes. For the homework, and I'm going to need my notes back one more time. Back and forth, I like it. For the homework, I would like you no calculators. Calculators are lame. Homework 4.7.1. You will find waiting lovingly on page 326. You get the privilege to work problems 1 through 17. Now I'm going to change that. We're going to say 1 through 4, 5 through 17 odd. That's it. That's it. Cool. I want you guys to start right meow. Baller. Hey, Raiders. Oh, goodness. He did. He wasn't messing around. I like it. Raiders, here, anything for the people on the road? Yeah. That's for tonight, by the way. Cool. All right. Later, Raiders. All right. In case you guys didn't have a textbook, here are problems 1 through 4. You can pause it if you need to see it. This is 4.7, page 326. There's 1 through 4. And here are 5 through 17 odd. Cool. Pause it there if you need it. And I will be taking this tomorrow.